The completeness axiom has many extremely important consequences, and in this video we're going to discuss some of them. First, the Archimedean property. This just tells us that the set of natural numbers is not bounded above. The next one, I call it kind of existence of our function, because what it tells me is that for any real number x, there exists an integer n, such that x is greater than or equal to n, and strictly less than n plus 1. So what it's telling me is that any real number is between two consecutive integer numbers. Feels obvious, but it's a consequence of the completeness axiom. And then the existence of a square root, the fact that for any natural number d, there exists a positive real number x such that x squared is equal to d, that is consequence of the completeness axiom. If you look at it, in the previous video I was saying that if I construct a set of all the rational numbers x such that x squared is less than 2, then the supremum of that set was the square root of 2. So that is going to be the idea that is used to prove the existence of square roots. Okay, I'm going to focus in this video on proving the first one, the Archimedean property, which is going to be extremely useful to us, especially when we're working with sequences. You're going to see that is going to appear over and over and over again. Okay, so we want to prove that the set of natural numbers is not bounded above. So the first thing that I notice is that this statement is written in a negative way, right? It's saying is not bounded above. But again, proving that something is not something is hard. So whenever you have a statement that is written in a negative way, you should start thinking, maybe contradiction is the way to go. Because if we do that, then what's going to happen? Well, we're going to assume that n is bounded above. And you see here again, I'm letting my reader know that I'm going to do a proof by contradiction. Assume for the sake of contradiction that the set of natural numbers is bounded above. And the good thing about this is that now that I have this assumption, I can use it, right? So what it means to be bounded above, right? Well, and how can I use it? Well, see, we know that n is not empty. We know it has 1, 2, 3, 4, 5, 6. It is not empty. N is a subset of the real numbers, and, well, is bounded above and is not empty. Well, we said that any non-empty set that is bounded above has a least upper bound by the completeness axiom. So that means that the set of natural numbers has a least upper bound. Okay, let's give it a name. I'm calling it alpha. Alpha is the supremum of the set of the natural numbers. Very good. But then, what does it mean for me? Well, by the definition of supremum, that means that alpha minus 1 cannot be an upper bound for n, because remember, alpha is the smallest upper bound. Okay, so alpha minus 1 is not an upper bound, and if it's not an upper bound, that means that I can find an integer k such that alpha minus 1 is less than k. Good. Okay, but if I do that, then what happens? Well, that would imply that alpha is less than k plus 1. Well, if you take a natural number and we add 1, we end up again with a natural number. So k plus 1 is a natural number. We have that alpha is strictly less than a natural number. That's a problem, because alpha was my supremum, so alpha was an upper bound, and the upper bound cannot be less than any element in my set. So that is a contradiction. It contradicts the fact that alpha is an upper bound. Okay, therefore what happens? Well, n is not bounded above, and that completes the proof. Okay, now you see, the Archimedean property is very, very important, and we're going to use it. But very often we're going to use it in a different way. It's written in a different way that is exactly equivalent. It means the same thing, but it's more useful to us. Because just saying that the set of natural numbers is not bounded above is not very useful in practice. But these two statements are very, very useful. So the first one says for every real number x, there exists a natural number n such that x is less than n. If you read at it carefully, this is just the negation of n is bounded above. Check it, but this is just the negation of n is bounded above. And now the second one says that for any positive real number, there exists a natural number n such that 0 is less than 1 over n, which is less than x. So in this case, if I pick an x that is very small, positive but very small, what it's telling me is that for an n sufficiently large, 1 over n is going to be less than x. And if you do the manipulations, try to see how you can go from the first statement on this slide to the second statement on this slide. It's actually quite simple. Try to think about how you would do it. Maybe think about changing the names of your variables a bit to make it clearer. But it's not a difficult proof. Give it a go. If you have questions, just please let me know. But I think you can do it. And this second statement is the one that is going to save our lives so many times when we're working with sequences. Okay, so now let's take a look at an example of how we can use the Archimedean property to our advantage. So here we want to prove that the set given by the elements that are of the form 1 minus 1 over n, where n is a natural number, we want to show that the supremum of this set is equal to 1. So how do we do this? Well, again, we have to do two things. We need to show that 1 is an upper bound, and then we need to show that 1 is the smallest upper bound. Usually what we do is that we pick any number less than 1, and we're going to show that that cannot be an upper bound. So let's see. As I said, first proof that 1 is an upper bound. So how do we do that? Well, we fix n, any natural number. And then, well, we know that n is greater than or equal to 1, particular is greater than 0. So 1 over n is positive. Good. Okay, but then if 1 over n is positive, then that means that 1 minus 1 over n has to be less than 1. Oh, that's it. That means that 1 is an upper bound for s. Good, done, I'm happy. Now, let's go to the second part. We're going to choose an L less than 1, and we need to show that L is not an upper bound. Okay, so how do we show that L is not an upper bound? Well, since L is less than 1, we know that 1 minus L is positive. Okay, that's the first thing to do. But now, by the Archimedean property, we can find a natural number n such that 1 over n is less than 1 minus L. No matter how small 1 minus L is, we can always find an n sufficiently large such that 1 over n is less than 1 minus L. Okay, but now this implies that, well, if I know that 1 over n is less than 1 minus L, this is the same as saying that L minus 1 is less than minus 1 over n. But adding 1 on both sides, I end up with L is strictly less than 1 minus 1 over n. So we managed to find a natural number n such that L is strictly less than 1 minus 1 over n. But that means, well, that L cannot be an upper bound for the set because L is less than at least one element in my set. And that concludes the proof of the fact that the supremum of my set S is equal to 1.